This is section 6.1, annuities. So an annuity is a sequence of payments made at regular intervals. The payment interval or conversion period is the time between payments, and the term is the time over which the money is to be paid. So when we're talking about annuities, R is going to represent our periodic payment, N is going to represent the number of payments made, I is the interest rate per payment interval. So you take your yearly interest rate divided by the number of payments you get per year. S is your accumulated value, and A is your present value. So accumulated means what it's going to have at the end. Present is what is happening right now. So to find our accumulated value, you take your initial or your monthly payment, so our R, or your periodic payment, times your accumulation factor. Your accumulation factor can be found in the table I've given you using your N, or your number of periods, and your I, or your rate per period. So we want to compute the accumulated value of an ordinary annuity of $500, which is compounded quarterly for 1 year at an annual rate of 8%. So in this case, our R, or our monthly, or our payment, quarterly payment is $500. Our N is 4 because it's quarterly. Our I is our interest rate of 8% divided by 4, which gives us 0.02. If we look at our table, we can use these two numbers to get our accumulation factor of 4.12161. So to find our accumulated value, S equals 500 times 4.12161, which is $2,060.80. Another way to look at this is to look at it every period. So notice this table represents the same annuity. It's just broken down per period. So each time your payment's going to remain the same, so this 500 column stays the same all the way down. The first payment period is going to be compounded 3 times. So if you, what happens is you're going to pay it at the end of the quarter. So at the end of first quarter, you pay the $500. It's compounded at the end of the second quarter, at the end of the third quarter, and at the end of the fourth quarter. So you can find the value at the end of the year by taking your R times 1 plus I to the number of times compounded. And then when you add those all up, you should get the total. So that's just a broken down version of the big picture number we got up there. The important thing to remember is that an ordinary annuity is payments are made at the end of our payment period. With an annuity due, an annuity due is at the beginning. So notice here that first payment was only compounded 3 times. Here it's 4. So each period gets that extra compounding time. So in the end, you do end up with more money total. So how that changes our formula is S now becomes R times the accumulation factor times 1 plus I. So let's calculate the accumulated value of an annuity of $100 invested at the end of the month for 1 year at an annual rate of 6%. So the end tells me it's an ordinary. So let's just find all of our values. So our R, our payment, is 100. It is 12 because there are 12 months in 1 year. I is 0.06, our interest rate divided by the number of periods, so 0.005. These two numbers, if you look on your chart, you get your accumulation factor. So our accumulated value S is equal to 100 times that 12.33556, which gives us an accumulated value of $1,233.56. The next one, suppose Ryan deposits $1,000 every 3 months into a savings account which pays 8% annual interest compounded quarterly. How much will Ryan have at the bank at the end of 5 years, assuming he deposits the money at the beginning? So the beginning tells me it's an annuity due, so we have that 1 plus I at the end. So let's find all of our values. Our monthly payment is, or our quarterly payment is 1,000. Our N is 5 years times 4 times per year gives us 20. Our I is 0.08 divided by 4, which gives us 0.02. We can use these two numbers to get to our table of an accumulation factor. So S equals 1,000 times our accumulation factor of 24.29737. And then since this is an annuity due, we have to multiply by 1 plus 0.02, 1 plus I. So we end up with $24,783.32. On this next one, how much must Sylvia save each month if she would like to accumulate $5,000 in 3 years? Assume her interest is paid at the rate of 6% compounded monthly and that Sylvia makes her deposit at the end of each month. So the end tells us that it's an ordinary annuity. We don't know our R in this case. We don't know how much she's paying. We're trying to figure out how much she's going to pay monthly. We know our total value, S, is 5,000. Our N is 12 months a year times 3 years gives us 36. Our I is 0.06 over 12, which gives us 0.005. So that helps us get our accumulation factor. Now let's plug in what we know. So our S is 5,000. It's equal to R times our accumulation factor of 39.33610. Divide to find that $127.11 is going to be our periodic payment. So present value is also called the discounted value. It's the amount of money which must be set aside to allow for a specified payment at after a specified period of time. And it's helpful for those who have a retirement fund goal. So if you say, I want to have this amount of money by the time I retire so that I can live, this is going to help you find out what you got to do now. So our present value formulas, it's pretty much the same, except now we're using a discount factor instead of an accumulation factor. Again, there's a table for that using your N and your I. So Bill would like to invest some money so that he can receive a monthly retirement supplement. How much money must he invest at 9% compounded monthly in order to receive $500 at the end of each month for the next 5 years? So the end tells me it's an ordinary. He wants to receive a periodic payment of $500. Our N is 5 years times 12 months per year, which gives us 60. Our interest is 0.09 divided by 12, so 0.0075. So we get our discount factor of 48.17337. So our A is going to be 500 times that value, 48.17337, which gives us $24,086.69. What if we make it at the beginning? Well, the only thing that's really going to change is if those payments are at the beginning. We get A equals 500 times 48.17337 times 1 plus 0.0075. That's the only difference. So we end up with $24,267.34. And last one, Jean's grandmother left him $10,000 when she died. So that he would not squander the money, she stipulated in her will that the money is to be invested in a bank account paying 8% interest compounded quarterly and paid out in equal installments every 3 months for a period of 10 years. How much will Jean receive each quarter? So we know our A value, our total value is $10,000. We're trying to find our R. N is equal to 10 years times 4 quarters in a year, so we have 40. Our I is 8% yearly divided by 4, which gives us 0.02. So we get our discount factor using our table. So we're going to set up in our equation, we know that the ending value is 10,000 is equal to R times 27.35548. We're going to assume it's an ordinary, so we don't have that 1 plus I. When we divide, we find $365.56 equals R. So Jean is going to be getting $365.56 every quarter.